Right now, you can open a chat box, type almost any question, and get back something startling. Ask one of today's leading AI models to write working code, compose a poem about heartbreak, or explain quantum mechanics, and it will, in about the time it took you to read this sentence. So, here's a fair question. How does it actually do that? And here's the strange part. If you ask the engineers who built these systems, people at the frontier labs, some of the sharpest minds alive, to explain exactly what happens inside the model the moment it answers you, they couldn't fully tell you. Not because it's a secret, because they don't entirely know. We have built the most powerful technology of the century, and we do not completely understand how it works. This isn't a conspiracy. It's a genuinely strange fact about how modern AI is made, and a small group of researchers is now racing to change it, to build, in effect, a microscope for the artificial mind. What they're finding in there is stranger and more beautiful than almost anyone expected. To see why nobody fully understands AI, you have to drop the way you probably picture software getting made. Normally, a program is written. A person sits down and types instructions. If this happens, do that. Every rule, every step, a human put it there on purpose. So if something breaks, you can open it up and read exactly what it was told to do. A modern AI model is not made like that. Nobody wrote the rules it uses to talk to you. Instead, engineers build something more like a learning machine, a giant network of simple, connected units, loosely inspired by the neurons in a brain. At the start, it's blank, useless. Its connections are random noise. Then they show it almost the entire internet and give it one deceptively simple job: predict the next word. Over and over, trillions of times, the network makes a guess, checks how wrong it was, and nudges its own connections to do a little better. There are hundreds of billions of these connections, and here's the key. Nobody chooses their values. The machine finds them on its own, hunting for whatever settings let it predict text well. Slowly, out of that endless adjustment, something remarkable emerges: the ability to converse, to reason, to create. So, a finished AI isn't something we engineered the way we engineer an engine bolt by bolt. It's something we grew. And anything you grow, you then have to study from the outside to learn what it actually became. We didn't build a mind. We planted the conditions for one and waited to see what came up. Now, using something powerful that you don't fully understand is not new. For most of the 20th century, we took aspirin without really knowing how it worked. It reliably killed pain. The precise mechanism stayed a mystery for decades. We used it anyway. For a long time, AI got the same treatment. It works, so ship it. And these systems are now woven into the everyday, drafting emails, writing code, helping doctors read scans, tutoring kids, shaping decisions large and small. But that's exactly why it works, don't ask why, stops being good enough. When a system this capable is making or shaping real decisions, you want to know what's happening inside it. Is it reasoning or just pattern matching? When it's confidently wrong, why? Could it be doing something we wouldn't want? And would we even be able to tell? You can't answer any of that from the outside just by watching what it says. You have to look inside. The trouble is, inside is hundreds of billions of numbers with no labels. For years, that felt hopeless, like trying to understand a thunderstorm by tracking the position of every raindrop. And then a handful of researchers decided to try anyway. The field is called mechanistic interpretability, a mouthful that means something simple. It's the attempt to understand the actual mechanisms inside a model. Not what it says, but how, internally, it arrives at what it says. It looks a lot like neuroscience. A brain is billions of neurons firing. We can't read a thought directly, so neuroscientists watch which regions light up and reverse engineer what they do. Interpretability researchers do the same to an AI, except they have a superpower no neuroscientist has. They can see every single artificial neuron perfectly and replay the exact same moment as many times as they like. So here was the first hopeful guess. Maybe it's tidy in there. Maybe one neuron stands for one idea, a dog neuron, a France neuron, a neuron for the color red. It wasn't that tidy. They found single neurons lighting up for a bizarre grab bag of unrelated things, and concepts you'd expect to find. A clean idea of the Golden Gate Bridge didn't live in any one neuron at all. The model, it turned out, was packing far more concepts than it had neurons, smearing each idea across many neurons and blending many ideas into each one. It was like opening a clock and finding the gears overlapping, sharing teeth, occupying the same space. Real structure was clearly in there, but it was folded up in a way nobody could yet read. The breakthrough came from a clever idea. If the concepts are blended together, build a tool that can unblend them. Researchers trained a second system whose only job was to pull that tangle apart into its underlying ingredients. They call them features. And suddenly, they could read them. In one landmark study, researchers mapped millions of features inside a real, deployed model and found genuine, specific concepts. Not just the Golden Gate Bridge, but abstract ones. A feature for buggy code, a feature for flattery, even a feature that lit up around the idea of deception. And you don't have to take my word for any of this. They wrote it down. A real, locatable feature with a number that fires on the concept of deception itself, not a guess about the model, a measurement of it. Here's the part that still gives me chills. Meaning inside the model has a geometry. Concepts that are related sit physically near each other in the model's internal space. Things tied to warmth and intimacy cluster in one region, things tied to computer code cluster in another. The model didn't just memorize words, it grew a kind of map where distance means similarity. Nobody designed that map. It built it on its own to make sense of the world through text. And once you can find a feature, you can do something wild, you can turn it up. In one famous demonstration, researchers cranked up the Golden Gate Bridge feature inside a model, and it became obsessed. Ask it for a cookie recipe, and it would route the recipe through the bridge. Ask it to describe itself, and it would insist it was the bridge. Silly on the surface, profound underneath. It proved the features weren't just labels researchers slapped on from outside. They were real, causal parts of the machinery. Turn one up or down, and the behavior changes in a predictable way. For the first time, we weren't only watching what an AI said. We were reaching in and touching the gears of thought. You've probably heard AI waved away with a shrug. It's just predicting the next word. And technically, yes, that's the job it was trained on. But researchers wanted to know, to predict the next word this well, what does it actually do inside? The answer broke the shrug. They watched a model write rhyming poetry. Common sense says it would write the line, then scramble for a rhyme at the end. Instead, looking inside, they caught it choosing the final rhyming word first, before it had written almost any of the line, and then building the sentence backward to land on it. And this wasn't a one-off. They traced the same behavior again and again, right inside the model. That's not reciting the next word, that's planning. The model had worked out, on its own, that good poetry needs a destination, and it aims for one. They found the same surprise in arithmetic. Asked to add 36 and 59, the model doesn't do the neat columns you were taught. Inside, two paths run at once. One roughly estimates the answer is somewhere around 90, while the other works out only that the last digit must be a 5. The two combine around 90, ending in 5, to land on 95. And here's the kicker. Ask it how it got 95 and it'll confidently describe the tidy school method. Line up the columns, carry the 1. A method it didn't actually use. It doesn't have reliable access to its own reasoning. It learned to do math one way and to explain math another by mimicking how people describe it. So it tells you a plausible story after the fact. Sit with that for a second. A model can do something genuinely sophisticated inside and be unable to accurately report how it did it. Which is a very good reason not to take an AI's explanation of itself at face value, and a very good reason we need to look at the machinery directly. So why does any of this matter, beyond being fascinating? Because if we can learn to read the inside of these systems, we get things we badly want. We could catch a model being deceptive before it acts. We could understand why it fails instead of just patching the symptom. We could check whether a system actually holds the values we intended, not because it told us so, but because we looked. Interpretability is, quietly, one of the most hopeful projects in all of AI. It's how we don't understand it slowly turns into we do. But here's the grounded truth, and it matters. We are nowhere near done. The features we can read today are a tiny fraction of what's happening inside a frontier model. It's less like having a full map of a brain and more like having identified a few hundred cells in something with billions. And the models aren't standing still. By the time we start to understand one generation, a larger, more capable one has already arrived. So, this is a race. On one side, how powerful these systems become. On the other, how well we understand them before we hand them more of the world. Right now, capability is ahead. The encouraging news, understanding is genuinely gaining. The field barely existed a few years ago, and it was just named one of the breakthrough technologies of the year. The honest news, it still has a long way to go. This is the part people at both extremes get wrong. The hype crowd says AI is basically magic, and it's all upside. The doom crowd says it's an unknowable black box we've already lost control of. The truth is more interesting and more demanding than either. It's a thing we grew that we're now learning to read, and how well we learn to read it is partly up to us. So the next time an AI answers you instantly and fluently, and it feels like magic, remember what's really happening. It's not a program someone wrote line by line. It's not a mind we designed. It's something we grew from an ocean of human text that built its own strange internal map of the world, that plans and approximates and sometimes can't even tell you how it did what it just did. And for the first time, we're learning to look inside and read it. That's not magic. It's stranger than magic. It's a new kind of science, and it's only just getting started.